In this video, I would like to follow along with Albert Einstein's famous paper on the electrodynamics of moving bodies. My intention here is just to give clarity to one of the most confusing parts of the paper on page 8. Here's a set of equations involved on page 8, and the confusing statement here, if x prime is chosen infinitesimally small. The trouble is he has already defined on page 7 x prime equals x minus vt, and it seems he's double using x prime as a coordinate and a variable of differentiation and integration. It's not an insurmountable obstacle. In fact, this is fairly common in calculus to say something like the integral of x squared with respect to x is 1/3 x cubed plus a constant. In fact, we should technically distinguish between the variable of integration and the limit of integration, perhaps just by calling it the capitalized version of the same variable. Well, without further ado, let's jump into some of the text of Einstein's 1905 paper on the electrodynamics of moving bodies, beginning with section 3. Let us, in stationary space, take two systems of coordinates, i.e. two systems, each of three rigid material lines perpendicular to one another, and issuing from a point P. Let the axes of x in the two systems coincide. So we'll have the other system maybe go like that. So this is the x coordinate, and their axes of y and z respectively be parallel. Let each system be provided with a rigid measuring rod and a number of clocks, and let the two measuring rods and likewise all of the clocks in the two systems be in all respects alike. Now, to the origin of one of these systems, system K, let a constant velocity be imparted in the direction of increasing x. Of the other coordinate system, K, and let this velocity, capital K, and let this velocity be communicated to the axes of the coordinates. The relevant measuring rod, so I'll put a little meter stick in here, and all of the clocks. So I'm going to draw just ignoring the x or the y and the z axis. Just imagine a space-time diagram, and we will have, this will be system K. It's just 2 dimensions now, so we'll imagine that meter stick being placed right here. This is the K's meter stick, and it is the front end and the back end of that meter stick are moving forward in the x direction, and this is going to be representing the t direction. So this is the time in, according to this clock in the K system. And it will be synchronized with any clocks over here, and so this is also t in the K system. Alright. So to any time of the stationary system K, there will correspond a definite position of the axes of the moving system. So you can see that the moving system, we'll call this x prime equals 1. This line will represent x prime equals 1, and this line will represent x prime equals 0. There will correspond a definite position of the axes of the moving system, and from reasons of symmetry, we are entitled to assume that the motion of K may be such that the axes of the moving system are at the time t parallel to the axes of the stationary system. So this axis and this axis are still parallel, and the z-axis here and the z-axis here is still parallel. We now imagine space to be measured from the stationary system K by means of the stationary, we'll put a stationary meter stick here with a big capital K on it. by means of a stationary measuring rod, and also from the moving system, little k, by means of the measuring rod moving with it. So that's this moving measuring rod here. And that we thus obtain coordinates x, y, z, and chi, eta, zeta. Sorry, it's psi, k, s, i, eta, zeta, respectively. So we'll be measuring, instead of measuring this as this will be measured in little x, little y, little z, and this one would be measured in chi, eta, zeta. Further, let the time t of the stationary system be determined for all points at which there are clocks by means of light signals in the manner indicated in section 1. But anyway, the way that we would draw this is that basically t, I'm going to call them the isoclines of t. This would be t equals 0, t equals 1, t equals 2, t equals 3, etc. So essentially, anywhere in the system K, I'd be able to determine the time on my clock by looking at the time at the origin and accounting for the time delay as light traveled from me to from the origin to me. For instance, if I saw that that clock said 3 seconds and I knew I was 2 light seconds away from that clock, then I'd know that the time at my position was 5 light seconds. Similarly, let the time tau of the moving system be determined for all points of the moving system at which there are clocks at rest relatively to that system by applying the method given in section 1 of light signals between the points at which the latter clocks are located. So if I had a light signal traveling from there to there, then this guy could determine his time by adding the distance from this clock in his reference frame in light seconds. To any system of values where of x, y, z, and t, here I just have an x comma t, which completely defines the place and time at an event in the stationary system. There belongs a system of values psi, eta, zeta, tau. So this could be a psi, comma, tau, according to, so obviously this x here is not going to be 0, but this psi, this would represent the psi equals 0 that happen to be the same at the origin. Maybe this is psi equals, I don't know, 2. And say this is t equals 3, and this line represents tau equals 2. And this point is tau equals 2. Anyway, the every system of values x and t completely defines the place and time of an event in the stationary system, and there's a psi, comma, tau, and an eta and zeta, determining that event relatively to system K, and this system K is traveling with respect to system capital K. So our task is now to find the system of equations connecting these quantities. In the first place, it is clear that the equations must be linear on account of the properties of homogeneity which we attribute to space and time. Well, what does he mean by linear here? I'm not entirely sure, but let's think about that. Let's think about that rod that is stationary in the lowercase k system, but is moving at a constant velocity in the uppercase k system. The lines of psi equals 0 And psi equals 2 here, representing the two ends of the rod, are straight or linear in the spacetime diagram for the capital K coordinate system. Now, the author is saying that it is also clear that the lines for tau equals 0, tau equals 1, tau equals 2 will be representable as straight lines in the spacetime diagram for the K coordinate system, capital K coordinate system. Okay, K is moving at velocity v. If we place x prime equals x minus vt, it is clear that a point at rest in the system K must have a system of values x prime independent of time, y independent of time, z independent of time. This is going to be a point at rest in the system K. This is not chi. This is not necessarily chi, but, and this is actually this probably is eta, and this probably is zeta. Whoops. But this x prime is not necessarily chi, because we might have a length contraction effect or something like that. Let's see. We'll first define tau as a function of x prime, comma y, comma z, comma t. To do this, we have to express in equations that tau is nothing else than the summary of the data of the clocks at rest in system K, which have been synchronized according to the rule given in section 1. From the origin of system K, let a ray be emitted. So this whole thing is, we'll call it x prime equals 0 for now. And let's call this over here x prime equals 1, because that's what they seem to be using down here. From the origin of system K, let a ray be emitted at the time tau sub naught. So this is tau sub naught, to be reflected along the x-axis to x prime. And that's kind of ambiguous, but I'm calling it x prime equals 1 because they have a 1 down here. And at the time tau 1, okay, I'll call that tau 0, tau 1, reflected thence to the origin of the coordinates, which would be like right there, at time tau 2. We then must have 1/2 of tau 0 plus tau 2 equals tau 1, or by inserting the arguments of the function tau and applying the principle of the constancy of the velocity of light in the stationary system. Alright, so the math doesn't say exactly the same thing as the text, so I'm going to have to modify this so that we have that origin at the same place. Because I'm assuming this is tau of x, comma, y, comma, z, comma, t. Although it might be x prime, but anyway, this would be the line x equals 0. So this is 0, 0, 0, and this would be the line t. Okay, and then so we would have tau sub naught would be tau at this event where x is 0 and t is t. Then we're going to have this point, which is, oh no, this is x prime, I'm sorry. This would be x prime equals 0. So I did have the right diagram before, because they're using x prime, y, z, t. So this is, and I would rather see why I want to use a 1 here instead. X prime equals 1 and x prime equals 1. So that it's the time from this event to this event, and then we'll have, this will be time t plus x over c minus v. I'm sorry, t plus 1 over c minus v. And then this time here will be t plus 1 over c minus v plus 1 over c plus v. I'm drawing these slopes badly because technically this should be a shorter amount of time. Let me draw that in purple. Kind of fix that. Should kind of come up this way a little sharper. About the same angle as that. So this would be tau 2 right here. And this would be tau of x prime equals 1, which is tau 1. This is that location, and the time there is t plus 1 over c minus v. Tau 1, which is, so it's x prime equals 1, y equals 0, z equals 0, and t equals t. See, and this is really confusing because he's overusing these variables. He's using t, well, he doesn't even define, but he's treating this the letter x prime as both a coordinate and a constant, which makes it a little bit more confusing than it needs to be. It was just a little more confusing than it needed to be because he had used x prime as the coordinate. Here x prime equals 0, here x prime equals x prime, which is 1. And now he's making it, and he's using it as the length of the rod, which is x prime here. Now he's making one more step confusing by also using x prime as a differential change element here. That might not be a third usage, actually. I think he's back to using x prime as a coordinate again. But he should never have used x prime as the length of the rod. He should have just called this, for instance, L prime or something along that line. L prime here, L prime here. Then we'll have L prime here, L prime here. Multiply this by L prime, and then put L prime here. So by putting L prime there instead of 1, that would make it based on however far it was from here to here. We'll just call that L prime instead of x prime because x prime is being changed. Now, I've taken the liberty of rewriting this equation from Einstein's paper in a more robust form with lots of extra little pieces of information. What's going on here is we have an emission event. Let's say emission. And then we have a reflection event. And a perception event. Up like this. And the time between the emission and reflection event is, if this is distance 1 here, then the time between the emission and reflection event is 1 over c minus v. The time between the reflection and perception is 1 divided by c plus v. Notice this is a shorter amount of time. And then that total amount of time is delta t from the emission to perception. So that's the sum of those. Now we're going to take that delta t of the emission plus the reception, and multiply it by this factor here, which tells us how fast the clock here is going. The traveling clock is going compared to the stationary clock. And notice this is a partial derivative. So when you have a partial derivative, it corresponds to something being constant. In this case, the thing that is held constant is x prime. X prime is 0, but that actually represents this line, x minus vt is 0. And this represents the line x equals positive vt. I'll write it as x equals vt. Now over on this side of the equation, we've got something else going on. We're taking this in two steps. The path in the s simultaneous direction, we're going basically from here to here. And what's going on here is we're going 1 unit in that direction. And we're taking how much time changes, how much the clocks on the meter stick in the K reference frame, how much do those clocks change as x prime changes from 0 to 1? Now we could just as well say del tau del x, where t is constant, because these two things would come out exactly the same. And it should be noted that x prime is not equal to psi. They're not. This isn't going to be the same, which is something established a little bit later on in the paper. But anyway, we're going to find out how much the time changes going from here to here, and then we're going to find out this part, which is going from this point in time to this point in time, and that is the time from emission to reception, delta t ER, emission to reflection, which is this right here, 1 over c minus v. And I should have put that in a box. There we go. That's the time between emission and reflection of this signal here in the in the K frame, or the capital K frame. So del tau is going to be in the lowercase k frame. So it's how much tau changes over this path plus how much tau changes over this path. That's what this calculation is doing. How much tau changes through space, and then how much tau changes over time. Then it's a matter of algebra. 1/2. I'll subtract this from both sides, so I actually end up with 1/2 delta TER minus a whole delta TER, which is, so it's going to be minus delta TER, 1 over c minus v, plus delta TRP is 1 over c plus v, equals del tau del x prime. And I guess we can invoke the linear part here. We'll just say when x minus vt is constant here, and we'll be saying when t is constant here, or x prime equals constant might be a better way of saying this, because then it makes these at least seem orthogonal, though they're not. they're not orthogonal. X prime equals constant, remember, went off in that direction, and t equals constant went in those directions. But anyway, this simplifies to c minus v minus c plus v would be minus c plus v over c squared minus v squared. And we'll be taking 1/2 of that quantity, which is c minus c is 0. Negative v minus v is minus 2v, so minus v over c squared minus v squared equals del tau del x prime. I left out the del tau del t. I left it out up here. Del tau del t. And so from there we can return to the text, which says del tau del x prime plus v over c squared minus v squared equals 0. So we can see what these partial derivatives indicate is that here t is constant, and here x prime is constant. It follows from these equations, he says, that tau equals a, that's an undetermined constant, I think, t minus v over c squared minus v squared x prime. And we also find that there are page 9, page 10, page 11, and page 12, 3.5 more pages before he actually has fully derived the Lorentz Transformation Equations. So I'm going to end this video here and possibly continue with the rest of section 3 in the near future. Thanks for watching.